Good morning, GMGM. Thank you, everybody here, for choosing to spend your time at our third inaugural NoirCon.
Welcome everyone to my talk. The talk is called the Noir Sniper Talk. Don't ask me why I named it the Noir Sniper Talk, like I just found that would be a good name for the workshop. But the goal of the workshop is to get your nerd sniped on client-side proving, Noir, and privacy. So first of all, like how many of you have like never written anything in Noir or like have never written a privacy? Oh, okay, perfect. Okay, perfect. So the goal is firstly to show you a little bit about like give you an intuitive model about client-side proving and what the how to think like rightly about the model of private computing. Then I'm gonna introduce the language, but then the cool thing is that we have like two really sick demos in this talk, right? So these are like real working demos, and yeah, like I hope, and I will like leave you with some really nice ideas. So yeah, let's get started. So firstly, who am I? I'm Harsh. I'm an exploration engineer at Aztec. My job is to build cool stuff. That's it. I build cool things with Noir and Aztec, and we have this small exploration team at Aztec, and our goal is to explore the design space on what's possible with these primitives that we are building. So the agenda for today. No, we are not gonna invent the AGI. The agenda is pretty simple. It's to nerd snipe you to Noir, so that when you walk out of this room, you feel like, oh, I really should write some Noir. I really should write some privacy software. So we're going to start with developing an intuitive understanding of ZK and client-side proving. Then we're going to go on ZK VMs versus ZK DSLs a little bit. A very gentle introduction to Noir, so I'm not going to read the whole documentation to you. I'm just going to show you what a circuit looks like, what does proving looks like, and then we get to the fun stuff, which is like cool demos, like showing you real things that work. Yeah, that's where like a lot of fun will be. And then I will leave you with some inspiration for what you can build with Noir, and not very simple things, like real things that I think can be fun, that can have some impact out in the world. And then yeah, like a small Q&A session if time is left. So yeah, so let's start. Everyone is hearing about ZK, everyone wants to get in, and everyone is confused. And that has been the state of zero knowledge proofs for quite some time. To just give an example of how confused people used to be back then about ZKs, I participated once in a hackathon. I made some privacy governance software. I won the hackathon, but they gave me a prize because they thought I made a ZK rollup, right? So like that's how confusing the state of like what ZK has been for people. And let's try to make it a little simpler. So what's the goal of zero knowledge cryptography? The goal is to allow proving of knowledge of information without actually revealing it. You do get some interesting scaling properties with it as well. We're going to talk about it. But you could say like in a privacy context, that's the useful thing, like most of the time, which is like it allows you to prove some knowledge of information without actually sharing that actual piece of information. So what does it look like? You have these two entities. You have a prover and a verifier. And prover possesses some knowledge, or some piece of knowledge, some information, and the prover doesn't actually want to give this information to the verifier, right? So, and the verifier is just interested in knowing that you do have the piece of information and it's correct, but they are fine if you don't show them everything about the information, right? So that's the real world interaction that we are trying to ideally enable with this. An example could be if anyone recently participated on the Aztec token sale website, there's a ZK passport, and like basically what you're trying to prove to the verifier here, which is let's say the Aztec platform in that case, is that you are a legal citizen of some country, and yeah, like you have a legal passport, and then you're doing a Face ID test, and you're not actually like sharing your actual data for that. And it's all happening client side. So that's the construct. You have a prover and a verifier. Prover doesn't want to share information. Verifier wants to verify the information, but it's fine if it doesn't seize it. Like it just wants to make sure that it's actually correct. So yeah, so that's what it looks like. This construct between them via zero knowledge cryptography is a ZK proof, which a prover has the ability to create and prove their knowledge of information, and the verifier can very succinctly verify. this piece of information. Now I said a bunch of stuff, but the question is, how is that even possible? Because yeah, I just basically described that's what it looks like, but yeah, how would this actually work? So let's take a small detour. Rather than talking about zero knowledge cryptography, let's talk about something that we all understand, which is computation. So what is computation? Computation is a step-by-step processing of information. You have inputs, you have like some processing done on it, and then you have an output, and that is computation, right? Now, if you look at multiplication of two numbers, you have an input x, you have an input y, you do some processing on it, which is multiplication, and then you get a result, which is, let's say here, x into y equal to z. So how do we verify computation as of now? And the classic way of verifying computation has been recompute. So the prover in this case, when they want to prove that they did a computation correctly, just gives the input, the exact computation, the output, and the verifier will be like, hey, here's the input, here's the computation that was done, I'm going to redo it again, and I'm going to see whether it's all correct or not, right? And hence recompute and verify, and you get verification of traditional computation. But the problem is, what if the computation gets really heavy, right? Like, so let's say you delegated someone to compute something for you, and it was very expensive, but now if the only way to verify that it was actually correct is recomputing yourself, that really sucks, right? So that's where we have this model of a verifiable computational model, right? Like, where what if we could prove correct execution? So what if we could like prove correct execution without like actually recomputing all of it? So that's a verifiable computational model, where every time you produce an output of any computation, you also have a proof of computation. And that makes the job of verifying computation really easier, right? So you could have an input, you could have a proof of computation, and you could have an output, and the person verifying your computation can just verify the proof of computation, which ideally has to be like taking less time and should be cheaper and faster than recomputing itself. And we have cryptography out there to enable this. So this model of computation, you can say, is a model of verifiable computation. But then the question is, how is any of it related to zero knowledge proofs? Like I just talked about verifiable computation. Like how does that give you any understanding of the ZK stuff? What if you could hide some inputs in your verifiable computational model? So what I mean by that is that in the old approach, when you wanted someone to verify your computation, you were giving them the input, a small succinct proof of computation, and then an output. But what if you had the ability to hide inputs, where you could say, here's the proof of computation, here's the output that was produced of it, but I'm not going to give you the inputs, right? And for example, take here, like what if we could have a computational model where we have x and y, which are the input, and then you compute on them, which is like the multiplication of them, and then you have this proof of computation. So if you have the ability to hide x and y themselves, then you have the ability to prove that you know 2x and y, which multiplied would result into a z, without actually sharing x and y. So this is the computational model that we use when writing client-side private software, where you give someone a proof of computation, you have the ability to reveal what information you want to share and what information you don't want to share. So in this case, like you can prove that you know two numbers when multiplied are 12 without actually sharing like what them are. So like if it's 12, then you don't know whether the person knows 4 or 3 or whether they know 6 and 2. So yeah, so the ability to hide inputs and be able to still prove computation gives you proof of knowledge of inputs, because the only way you could have produced the proof of computation is if you knew the correct inputs. So that's the model of how you write like provable software, like in private software. And this ZK cryptography gives you two primary properties, which you also get with Noir, where you can prove knowledge of information without actually sharing it, like being able to hide certain pieces of knowledge and still being able to prove properties around them. And then also the ability of scalable computation, where you could like prove something once and then it can be verified as many times wherever you want in very succinct time. Yep. Cool. How do we write a ZK program? Currently there are two ways to do it. One is a ZK VM way of doing it, where you have a virtual machine. So it's like RISC-V, it could be a ZK EVM, and you just write your computation once, And yeah, then it like the ZK VM has a circuit, and then your computation gets proven. Like I don't think like a lot of ZK VMs right now are actually ZK. Like I don't think like if a lot of them give you the ability to actually hide your inputs, like not sure. But the examples are SP1, RIS0, Cairo, Lita, which is like a custom ISA. But the thing is that you can like take a language like Rust, C++, and then you write your computation once in them, and then you have this virtual machine which is capable of producing ZK proofs. And then the second way is of a ZK DSL, which is what we use with Noir, where you write it in a custom DSL language, which is like Noir, Circom, etc. And then it compiles to a ZK circuit. And then you can use any proving system you want, and then you can prove the knowledge of inputs, you can prove correct execution with it. So yeah, that's the ZK DSL approach. And here's a small comparison between both of them, but it's pretty intuitive. Like a ZK VM is, you have a virtual machine, anything that can run on the virtual machine can be proven. In case of a ZK DSL like Noir, you write your circuit in a domain-specific language, and then it gets proven later on. Okay, so about Noir. So finally we get to Noir, since we now understand the model of private computation. It's a Rust-like looking language. So if you know Rust, you already know Noir, I would say to some extent. So a lot of you might ask, then why even not like just use Rust? It's because like Rust has a lot of features that you just don't need. Like Noir is like, it looks like Rust. It has the most important feature sets that you need. But then, for example, you don't need dynamic dispatch in Noir, in a language like Noir. So like, there's no point trying to do that. So yeah, so it's a Rust-like syntax language. It has an intermediate representation. So any Noir program compiles to Acer, and it's an intermediate representation. Any prover that works with Acer also works with Noir. And then it's highly optimized for client-side proving. That's where the edge is. Like before this, we only had Circom, and it's a very complex looking. Like, has anyone here written like anything in Circom? Like, has anyone? Oh yeah. So like, if you all know the pain of writing Circom, right? Like, it looks like this very alienated, hard language. Doesn't look like anything that we have mostly written our computation in. So yeah, Noir is very Rust-like, very high level. It has a rich standard library, and yeah, rich ecosystem of apps, and it's maintained by the OG Aztec team. So the high level pipeline of Noir is that you have a Noir program. It compiles to Acer, and then you can execute it. So like, the process of executing it is basically generating a witness, and then any prover which is compatible with the Acer representation and the Noir pipeline can then go ahead and prove it. So yeah, so that's like the high level pipeline. And let's look at a real like working Noir program. So I'm gonna open my cursor. Is the code visible, or is it like too small for people at the back? I need to zoom out. Okay, cool. Is this better? Oh yeah, cool. Let me try to make it fit. Screen real estate management seems to be quite a real problem. 1 second, come on. Okay, cool. Now I think it should be good enough, right? Like visible for everyone now? Okay, cool. So here's what a Noir program looks like, right? Like it has, if you've written Rust, just like main, you have a main function which is the entry point for your binary. Like here you have a main function which is the entry point for your circuit. And then you have an like you can have like any sorts of input configurations that you want here. So for example, we have this input here, and you see this word field. So field is a fundamental data type in basically any ZK cryptographic construct. Just like you have a U32, U64, we have field elements here. Field elements have their own properties, they wrap. So for example, they have a certain bit size and a specific prime number till then which they go. And if your computation overflows from there, rather than throwing you an error, like the number will wrap. So it's basically modulus happening there. Like you're basically working in doing mod every time the number overflows. But for now, like just think of it as like an unsigned integer. And in most of your cases, you won't even overflow the size of the field. So right now, just think of a field as an unsigned integer, but it has some special properties. In case of an overflow, like the number would just wrap back. And then here's the written of your is the written value of your circuit, which for now is a boolean, so a true or false. So what is our program trying to do? Our program is trying to check that if a given input here belongs to one of the elements inside the array. So like this is an array of 5 field elements, 1, 2, 3, 4, 5. So you can think of it as checking some sort of a membership proof in a list, and then you loop through the length of the array, and then you check if one of the elements in this array is basically whatever the input value is. So it can be very useful in certain scenarios where you want to do membership proof checks and things like that, right? So yeah, that's basically what a Noir program looks like. Now you might have seen this one word called public, and the word pub or public means very different in Noir than what it means in Rust and most of the other languages. Public means that this piece of information will be shared with the prover. And since we don't have the word pub before our input, this piece of information won't be shared with the prover. So when we would run this circuit right now, and when we would prove it, we won't actually be sharing, we won't actually be sharing this input element. So basically what we would be proving is that I know one element, which is either 1, 2, 3, 4, 5, but we won't actually share which one it is. And the verifier would know that you know any one of the elements out of these 5 elements, but the verifier won't know which one you exactly know, right? So yeah, let's test it out. So the first step is, so you can download the Noir tool chain later on from here, and everything is available on my GitHub. I can share it at the end of the talk, but yeah, like this is how you can install it. There's no need to follow along right now. You can just watch me doing it and later on try it for yourself, but we have separate Noir docs, so feel free to visit them. So yeah, like we are gonna do, the first process is to compile your circuit. So you do a compile, and yeah, basically what happened here, I think we can bring back the file explorer. Oh yeah, I can delete the target folder so that I can see everything happening from scratch. So I come and I say now go compile, and then you see a target folder has been made, and we have a compiled circuit, right? And then this has like a lot of intermediate data that is then needed to generate witness and proving stuff, right? And then you see there's this file called, so we also have to run this command called nago check, and this will generate this file called prover.toml. So let me do that. Yeah. So once, yeah, you would have to like, right now I already have the file, but when you would run it, like it will generate a prover.toml, and this has an input field here that I can set to whatever I want. Right now it's set to 7, but whatever I will assign as the value of this inp would be whatever would be the value of the input here in this main function. So for now, let's try a real scenario where it should work. So let's say I'm gonna say, yeah, I'm gonna say I know an element 2, and then I'm gonna, second, it looks like I have shifted to Greek. No, oh yeah. So I'm gonna, let's say I know an element 2, and then it's part of the list. So like when I'm gonna prove it, it should actually work. So the first step is to generate a witness, and a witness is basically an execution of this circuit with some specific data. So in our case, it is execution of the circuit with this input data 2, and then when we see here, like we have generated this file called this .gz file, and this contains the witness data for this specific circuit. Why is it not showing up in my target directory here? It's interesting. Second. Oh yeah, it's here, but like it's not actually showing. It looks like the cursor isn't updating, but I can see it on the CLI that the file does exist, right? And then the second step is, yeah, then the second step is actually now proving it. So we did now go execute, and then we can use a prover which we have, which is BB, which is the prover that is maintained by the Aztec team. You can check out our GitHub, the installation instructions are there, and then now I can generate a ZK proof of this witness on my device locally. Just a second. BB proof, and then yeah, I'm saying that the circuit file is here, and then I'm saying this is my witness file, the specific execution of the circuit that I want to prove, and then put the proof in the target directory. So now when I do this, again, it looks like my directory isn't updating here, but if we go and say ls target, we can see that there's a proof file and there's a public input file. And the public input file is whatever is the public information related to the circuit, which is the written value. And while the proof file itself is basically the ZK proof that the prover can use to verify. So I can say bb verify, and then I can, so I have to now firstly generate a verification key. So I can say bb, what's it is, yeah, I think, yeah, bb proof, and then there's this thing called bb verification key, yeah, bb write vk, right? So now this will create a verification key, and a verification key is a key that you use to verify the computation of the circuit. So yeah, so we now just created this specific verification key, and now this verification key is also what is used when you use when you're verifying your proofs on chain, let's say on a solidity contract. So you have the ability to verify the proof here. So I'm gonna say bb verify, and then second, yeah, so like I'm saying that this is my verification key, this is the part to my proof, these are my public inputs. Let me bring it back, okay. And then when I do this, this says proof verification successful. What if I try to play with the prover? What if I try to play with it to say that I actually know an input, let's say 3, which belongs to, like I know an input 3, but let's say if I actually don't know it, like I don't have the proof for it, right? So what would happen in that specific scenario? The prover will actually fail to verify it. So let me show this around to you. So what if I say, yeah, just a second, like inputs. Oh yeah, let's say I try to prove, let's say I have a prover like an element 7, and I'm trying to say that 7 belongs to this list. And then what I'm going to do is I'm going to copy this old public input file here, and then I'm going to quickly generate, I think every time I type it, yeah, it gets out, but yeah, like I'm super quickly going to execute like create a new witness, and then I'm going to prove this specific witness. Oh, it has to be bb proof. And then if I will now try to convince the verifier that I know an element 7 which belongs to the list, though, so by dropping this old public input file here, it will fail. So if I will come here and if I say, yeah, replace it with the old file, I'm trying to like spoof the verifier here, it won't work. It will say, no, you don't know this. Yeah, you can see that it says, yeah, just a second, it says that the verification failed and the proof verification failed. So you can't, yeah, you can't fake proofs in here. Cool. So that's basically a very quick demo of how like writing a circuit works, how verifying proof works, how everything else works. But now I'm going to show you like some real fun stuff that we have made with it, right? So if you go to this thing, and you can probably play it on your laptop as well, like it's already working on this link called privacy/pool.versal.app. If you type it on your laptop, it should pop up on your laptop, and you should be able to play with it. What it is that it's a privacy pool implementation in Noir, and it's already live. And basically the way it works is it works like just like how any privacy pool works. So you can create nodes, but what you're doing essentially on this app is that you can deposit into a privacy pool, and then you can withdraw from it by creating a zero knowledge proof that you made a deposit to this privacy pool, and you have the ability to withdraw from it without revealing anything about your address. So for example, imagine it as like a ZK like debit card, right? So I can come and deposit to this application, and it processes my deposit, and now I have $50 in this privacy pool. Everyone else can come and deposit their balances as well. So in case of a debit card, like every user's balance can be on this pool, and that every time you want to spend from this debit card, you can generate a client-side proof. So if I come and show you what happens on the console, you can see that you basically are creating nodes, and you are putting these nodes inside a Merkle tree, and then you have the ability to prove that you have one of the valid entries inside this Merkle tree. So you have the ability to basically withdraw from the pool and spend it. So for example, I can spend an amount, let's say 50, and I can say withdraw, and now it's generating a client-side proof. So you can see generating proof, and the proof is done, and the withdrawal is done, right? So yeah, I think let me use. Okay, cool. Yeah. So yeah, so basically this is a privacy pool that we made. It does client-side proving, and you can check the open source code out. It's on my GitHub. So if you go to my GitHub, which would be Bajpai 244, and the whole code is available open source for you to check it out. So second, I think my internet here is a little slow. But yeah, like I can later on share it on my Twitter as well. It's on my Twitter, pinned there as well, the code, like the whole source code. Cool. So that's about like a privacy pool in Noir. But let's look at like, so this is like one of the prototypes that I've shown you that we have built, like a whole working privacy pool in there. Then what are other people building with it? So we have like a team called ZK Passport, which have been able to create client-side proving of password information. This is what we have also used on our own platform at Aztec to prove that you have a valid passport and to be able to do identity proofs without actually sharing any of your specific information. So we do have the ability for that. And then ZK Passport team is pioneering it. Then we have the Pay network. It is a debit card, and it allows you to pay anywhere with your card, but then the transactions are not visible on a block explorer, because with other cards out there, it's all available. So if you're like using a card on a Gnosis chain, like the whole explorer has everything available. You can go and see that someone is spending $2 here, $5 here, and then like you could basically use all of this information to get all of this micro details about these users, and it's just like out there naked on public blockchains. While Pay uses Noir, and they have been using Noir to create a private payment processing network for this. And yeah, Noir is being used there. Then we also have this team called ZK Email, which is again written in Noir, and it allows you to prove stuff with Noir. Like prove stuff about your email with Noir. Like prove that, let's say you want to prove that you have worked at a specific company, you can just prove that you had an email from them, that you actually joined it, and that should give you a proof that you actually did work there. So what are some cool things you can build with Noir? Yeah. Second, I think it will be back. Cool. What are some cool things you can build with Noir? Like build a client-side provable game. Has anyone here played like Dark Forest? Like it was a game that used to be on XDAI. Yeah, like I think like someone should just redo it again in someone should definitely redo this game again in Noir, because it was so fun. Back then it was written in Circom, if I'm right, and I would love to see if someone would like redo this game in Noir and bring all the client-side proving that we have in here. Like this is like just a fun stuff. I don't think like this is like, it's just fun. Like I've always been thinking that a lot of people have been writing ZK EVMs, and I was like, oh, what if someone writes just an EVM interpreter in Noir, like you get a ZK EVM. But again, this is just a fun idea. I'm not saying that, like it would be the best one, but yeah, like this is also a fun idea. But like another cool one is taking Noir to new proving systems. So basically right now, Noir works really well with our BB prover and our proving system, but I think it can be pretty interesting to like hack it up to Halo 2, like hack it up to Starks. I don't know, like a Starkified Noir. But yeah, like you can do all of this really cool, fun stuff with it, because Noir itself is very extensible, so you can just like extend it to any proving system that you want out there. So that's something really fun you can do. But here's my favorite one. My favorite one is build privacy applications, and that's the one that I really enjoy. So like I started my career in crypto, in privacy, like 4 years ago. I was working on a ZK DID protocol, and back then like no one really cared much about it, like to be honest. But now I think people do, and that's why I think that's my favorite thing to do with Noir. That's what I started learning Noir for, right? So my coolest thing is to build privacy applications, and I think the best place to build it right now is with Aztec, because Aztec allows you, it basically gives you the ability to create private Ethereum-like applications. So right now when you're out there and developing on Ethereum, and when you're developing something like Uniswap, every trade is public. But Aztec gives you a primitive to decide what you want to be public and decide what you want to be private. Noir is the smart contracting language on Aztec. So if you know Noir, you can basically program Aztec with it. And then you can basically build a private DEX, a private lending market, and you can do all of those things on Aztec because it's a private world computer. You can decide what you want to be private, you can decide what you want to be public, and that's what I really think is like some of the coolest things that you can do with Noir. Yeah. So another demo time. Now I'm going to show you something really cool between Aztec and Zcash. So how many of you have heard like about Zcash here? Like, okay, cool. I think, yeah, that's nice to know like that a lot of you have like a lot of you know about it. Yeah, it's something that like has been, it's a very old project, like I think more than 7 or 8 years, and now suddenly it's the one that has like been in a lot of hype. And Zcash allows you to do private transfers. So you can do private transfers with it, right? But it lacks programmability. Like you can't program it. So I wrote this piece of article where I was like, okay, Zcash has programmability. Zcash has just the ability to transfer assets, and Aztec has programmability. Like you can do private programming with it. What if you could like use Zcash on Aztec? And that's an exploration project we did. Like, can you privately use Zcash with Aztec? Can you have Alice and Bob in a situation where Alice can privately, let's say, sell her Zcash on ZEC and get back privately some USDC on Aztec without Alice knowing who Bob is on Aztec, and without Bob knowing who Alice is on Zcash, and without the person or the app which is facilitating it knowing who Alice is on Zcash and who Bob is on Aztec. So like complete end-to-end privacy. I think this demo is gonna be tough because it requires internet, and it looks like the internet right now is very low. Let me just check. Is it just because of my mobile? But yeah. But then the construct that we're gonna use here is one of a partial note. So basically, Aztec has this thing called partial notes, and they basically allow you to receive payment from anyone without revealing your Aztec address. So for example, rather than saying, hey, give me my USDC on this specific address, because of Noir and Aztec and the way we have designed our private state, you can say, hey, give me my USDC on this cryptographic information, which is a partial note. I will receive my USDC, but you won't know my address. You will only know that you paid to a partial note, but my partial note cannot be linked back to my address. So that's the primitive we're going to use. Alice is going to privately send her Zcash to an intent solver on Zcash, and then Bob is going to give the partial note to pay on Aztec, and this way Alice would be able to pay Bob without Alice knowing who Bob is and without Bob knowing who Alice is on their respective chains. So let's do this demo. I hope it works because it requires a little bit of internet, but let's see. Yeah, so we have this interface, and then for the Zcash side of things, and then we have this interface for the Aztec side of things. So this screen is the screen for Bob. This is where like you can see Bob's current Aztec USDC balance is 0. And then let's say Bob did some really hard work and now wants 100 USDC back for his work from Alice. So what Bob's gonna do is Bob's gonna create a partial note address to get 100 USDC from Alice. So we are generating and this is happening on the Aztec sandbox. So I have an Aztec sandbox running in the background for me. So let's wait. Yep. So gonna happen soon. Oh yeah, it happened. So like you can now see I have this like address to a contract that holds partial note of Bob, and then Bob's, let's say, has given it over Signal or any chat application this partial note to Alice, and now Alice is on this application which allows her to send USDC to Bob by selling some of her ZEC. So what the app is saying to Alice is that, hey, if you pay some amount to this address, I'm gonna pay whoever you want on Aztec 100 USDC. So I'm gonna put, Alice is gonna put the partial note of Bob, and then she's gonna put, I need you to pay 100. And then Alice is gonna copy this address, and she's gonna go and open her Zcash, her favorite Zcash app. So for me right now, I'm running an Android emulator, and then I will come here and I will say I want to send some amount, and it's happening on testnet. Don't worry, I'm not burning real ZEC for this, but yeah, that is going to send something like 0.01, and yeah, she's gonna send it. And now what has happened is that Alice has sent a private transaction on Zcash to this intent solver. And she's like, okay, so yeah, like it's client-side probing. Let's just wait for this to happen. Yeah, so now the transaction has been sent. And now it has sent the intent solver to give Bob back 100 USDC privately on Aztec. Now Bob is currently waiting for confirmation. It's waiting for this transaction to actually get included in Zcash. So if you go and look at the current testnet of Zcash, the block explorer in there, there should be something in the mempool. So yeah, here's a transaction. The transaction is in the Zcash testnet mempool, and the moment it will be mined, which should be like in 30 more seconds, we will get like one confirmation. Then like the intent solver is gonna give Bob some USDC here. So let's just wait like for 10-15 more seconds. If you want to look what's happening in the background, you can see that the software of the intent solver is looking at the shielded balance and is seeing if the balance is being completed or not. So it looks like the block has been mined. Yeah, you can see the confirmation is there. And then what the solver did is that the solver paid back to the partial note of Bob. So now Bob privately has 100 USDC. You can see the balance has been updated. And yeah, this way like they are able to do a completely private swap between each of them without like knowing who is who on both of these chains. And that's something that we made as well. It's available on this repo called Zcash Aztec Private Swap. So we have this thing called Aztec Pioneers, and we experiment and build cool things on Aztec on this specific GitHub box. So if you have like some cool idea, more than happy to put it here. All of the source code is available here for all of the experiments that I've shown you. We also have an OTC desk. I'm not gonna demo that, but it gives you the ability to do private OTC, like being able to privately swap whatever tokens you want. So yeah, so that's basically another demo. Coming back to, yeah, so you can like do way more than this. You can basically build a private lending market on Aztec. You can build private DEX with Noir on Aztec, private lead aggregators, like an Aztec L3 with Noir. You can probably do that. So yeah, there's like so much more to do. And I'm gonna end this presentation by saying that we should, like the reason why I'm very excited for all of this and why I like spending my time on all of this is because like it's the right time to do privacy. Like finally people do care. Everyone is talking about, oh, Bitcoin is transparent, and that's why let's say something like Zcash is getting adoption. And now suddenly everyone does care about this thing, and it seems like there is a market out there for people who really want to transact privately and use their DeFi privately, do all their financial activities out there privately. So I think it is the right time to build such software. And it's like when people are going to look back at this time, and when they're going to look at Noir and Aztec and all of the privacy stuff that's being built out, they're going to look at it as a really cool time. That's like every day I look at like privacy software and zero knowledge cryptography, it seems like something out of science fiction, and I think it's pretty cool to build with it. So I'm going to say the possibilities are endless, and thank you for spending your time with me. I will be around here. Let me know. Yep. Yeah. Oh yeah, we can have a mic here.
So why do we need like another language like Noir? Like why can't we just use plain Rust?
Oh yeah, I actually answered it like in middle of my presentation. I was saying that like you don't need the whole feature set of Rust. So for example, you don't need something like dynamic dispatch, right? Like Rust has a lot of features that you just don't need to build a privacy language. So for example, just take dynamic dispatch. Then for example, you could say lifetimes and all of these concepts. You don't need it to write provable software. It's just gonna complicate your language. So yeah, and then go ahead.
Well, yes, but you do have to create like a developer community around your new language, while Rust has that already. Also, the AI is very much trained on AI on Rust.
Yeah.
So I think it does provide a lot of value.
You want to
just
answer
keep
this?
it in Rust.
I think Zach wants to answer this.
Can I feel that one? Sorry. The stage. It's a very good point, and like what Harsh was saying about like the restricted set and the simplicity, I think is very valid. But you're also right that like there's an enormous amount of canonical like work around how to write idiomatic Rust, a lot of reserving resources. A huge reason why we decided to make our own language is because we wanted the ability to add in very specific semantics for how to write private programs that didn't exist in Rust, that would have required extending the language to the point where it would have been unrecognizable. Specifically, we have a lot of keywords in Noir to do things like utility functions where the code being executed is not being proven and you're just computing witnesses. And fundamentally, part of it is about how to write idiomatic ZK programs. Like, checking a computation has been performed correctly is a little bit different from doing the computation. And often, like, the checking part is actually a lot faster and more efficient. So it kind of changes a little bit about how you want to structure your programs. We have certain, like, keywords that aren't present in Rust. We wanted to extend our macro system to do metaprogramming in a way that Rust doesn't support. So we were either looking at building our own language from scratch, or like heavily extending Rust to the point where we wouldn't be able to say in good faith, oh, it's just Rust, because it wouldn't be anymore.
Any other questions?
So in order to make private transfers between accounts, I understood that a contract was deployed, right?
Yeah, you're correct.
And can you trace who deployed a smart contract? Otherwise, yeah, it just doesn't make sense.
Oh, you're saying like, can someone trace that who deployed the smart contract on
Yeah.
Aztec?
Yeah.
Oh yeah, like it's upon you if you want to make this information public or not. So let's say there's this concept of being able to deploy a contract privately. So basically Aztec has this thing of where like you decide if you want to emit this information that you've deployed this contract or not. But if it's a purely client-side running smart contract, then and if you don't actually like make it public, like the contract deployment is also possible privately. So like yeah, like in our specific scenario, we don't basically public emit that we have deployed the smart contract. Like it's out there in the private state and no one knows that it has been deployed. So no one else can discover it unless we consciously want it to happen. So in our scenario, it was private.
Okay, and another question, if the idea is to make it as private as possible, how do you transfer, I know it's like a really specific example, but how do you transfer the information of the escrow basically privately?
Oh yeah, so like, they are like, so basically that's a question of, like what mode of communication you use,
Yeah,
right?
yeah.
And you could use two mode of communication, right? Like one is which I said, you could just basically give the address of the escrow or like your partial node address or over signal to let's say someone like Alice, and it's end-to-end encrypted, and it's basically free to send this information, and then she can just use it to pay you. And that's, let's say, how you both discover this information. The other way where, let's say, you don't want to exchange, let's say these like such a mode of communication could be that Alice could have a public key, and then let's say, so Bob could have a public, Alice could have a public key, and then Bob could privately log an encrypted log of this information, encrypted to, let's say, Alice's public key. Alice could be watching Aztec and then could decrypt this information and should be available.
Okay, thank you.
Yeah.
I just say that your presentation is very cool, man. It's a great topic and hard topic for you simplify for us. And then thank you. Congrats for your presentation. Okay.
Thanks. Yep.
The witness, right? What kind of information does that store conceptually versus what the prover does or the execution of the program?
Yeah, so so witness generation is basically it's information about the specific execution of a circuit with some information. So let's say when we saw that specific circuit execution with that specific input of 2 or 3, right? So then like there's information that's very specific to executing that circuit with that input, and that's like all the information that the witness has. And the goal of the prover is to then basically generate a proof around it with the ability to hide, let's say, information that's not supposed to be public. So let's say witness is when you have like, yeah, witness is basically the result of execution of a circuit with specific information. And yeah.
So that would be specific to the prover engine, the witness.
Yeah, that's information for the prover. That's not information for the verifier. So the prover then takes this information and creates a ZK proof out of it. If that helps, or are you asking that is it like is the format itself tied to a very specific prover?
I guess Noir is like a DSL of
Yeah.
sorts for the underlying prover engine,
Yeah.
right? So the witness, if I was using a different DSL to write Stark proofs, they would generate the same witness file.
If you're using a different DSL to write, so Noir is not a proving system here. So let's say if you're using a different DSL, let's say something like Cairo, your witness would look different from what Noir would generate.
Okay.
Like with ACR, yeah.
All right, thank you.
Yeah, it won't be the same. Time is over. We got one more.
Thank you. That was great. I was curious more of like practical side. So let's say as an app developer, right, like privacy app developer, and I am bullish on Aztec, but say Aztec is still going to bootstrap its liquidity, user base, etc. Right. So I'm curious to hear your thoughts on how do you guys plan on to, like, what set of tools do you have, maybe like bridges, etc., to sort of get the existing liquidity from Ethereum and other chains that could be used on Aztec for us as app developers to make it easier to bootstrap?
Yeah, although this question is not very specific to the presentation, but
Yeah.
I will still say that we are actually doing this experiment in our exploration team where we are exploring that can you initially use an Aztec wallet to, let's say, swap on other public chains while like still keeping this information private on Aztec's side, that let's say who made the swap. So for example, have you used Zashi, like the Zcash wallet? Yeah, like you can, let's say, use Zashi and you can like right now go and swap whatever asset you want. You can do similar techniques with Aztec with complete privacy. On the Aztec side of things, you can basically have an intent protocol where you express your intent, you lock your funds, and then you say whenever the intent is complete, please pay back to my partial note. So this way someone can go out and solve your intents for you, which could be, let's say, swapping, lending, and all of those things. And then they can pay back to your partial note address and then still fulfill your intent. And so basically you could swap on Jupiter while being on Aztec, because you could say, hey, like I have one Sol, I want 100 USDC. And then you express this intent privately, and then someone will go on a public chain, do that swap for you, and then give you your 100 USDC or whatever it is privately on Aztec. And yeah, so you can technically do that. Like that's the way to go.